Okay, we continue looking at isomorphism and also develop another concept called automorphism. One thing that we come to see, abelian groups of order n are classified by which group they're isomorphic to. So the question is, suppose you have the product group Zm cross Zn. These are prototypes of cyclic groups. Basically, all cyclic groups are isomorphic to the integers mod n, or finite cyclic groups, I should say. So how many elements are in here? Well, there's n times n elements. So when is the product of those two cyclic groups cyclic? We have seen Z2 cross Z2 is not cyclic. It's not, that four element group, the client 4 group, is not isomorphic to the 4 element cyclic group. And just recall, I think I forget the terminology if I use this group G cross H. I think I called the product group. We looked at that very early, or maybe I even called the Cartesian product. A more common terminology is called the direct product of G cross GH. So Cartesian product, direct product. Usually Cartesian product, maybe when we're thinking of it as just a set. Usually if we think about the group, the product group, that's called the direct product. So let's answer this question. These two groups are isomorphic if and only if M and N are relatively prime. If and only if the GCD of M and N is equal to 1. And so clearly that's not the case with Z2 cross Z2. The GCD is 2. So let's try to prove this. So one way, what we're going to do is we're going to prove the contrapositive. So what we'll prove first is that, I better restate this. Certainly, I mean, Z mod n cross Z mod n, those two groups are isomorphic, well, if and only if they, M is equal to n. So what I meant to say is the direct sum of xm cross xn is cyclic, and so isomorphic to Zmn if and only if the GCD of those two are equal to 1. So we're going to prove it. We'll show that if the if we have this isomorphism, then the GCD is 1, So we're going to prove that implication by demonstrating the contrapositive. That if the GCD is not 1, so equivalent, that's to say it's greater than 1, then Zm cross Zn is cyclic. And so that'll prove it, because if we can prove is not cyclic, because cyclic, a cyclic group, saying this is cyclic is the same, Zm cross Zn is cyclic, is the same thing as saying it's isomorphic to a single integer mod nm, one single group, Zmn. And so basically to prove A implies B, you can prove that by proving not A implies not B, not B implies not A. So we'll assume the GCD is not equal to 1, and we'll prove that isomorphism. So suppose the GCD of M and N is some integer G, which is greater than 1. So M over D and N over D are both integers. And so certainly Mn over D is also an integer with 0 is strictly greater than M and D, strictly less than Mn. I think I have a little bit extra space here, so let this pair be in Zn cross Zm, Zm cross Zn. So that equivalence class A is in that equivalence class A is in Zm, and that equivalence class B is in Zn. Then if we look at this, and this is an integer, and let's add that group element to itself this many times. And so the way we add is we just add each component. But here we would have ND over MA. Here we would have M over D NA. But that's got to equal the identity in that direct product group, in the product group, because this is the identity coset, in the identity class in Zm. This is the identity class in Zn. But notice for that integer, unlike arithmetic, we can think, okay, 1/2 we can multiply. In a group, when the order is addition, you can only multiply by a whole number, right? So it wouldn't make sense for n over d to be a fraction. That has no meaning in putting any number in front of a group element. But putting an integer in front of the group element means you're adding it to itself a repeated number of times, and those are both integers. So what does that tell? So that tells us that every element of the product group, that's what AB was a typical element, has order at most Nm over D, which is strictly less than Nn. So no element can generate the entire Mn elements of that product group. And so that group can't be cyclic. And so it's not isomorphic to a cyclic group. Right? The integers mod any one number is cyclic. So it's not cyclic because it can't be. So it's not cyclic, so it can't be isomorphic. So we proved that if the GCD is not equal to 1, then Zn cross Zm is not isomorphic to Zmn. So that's equivalent to proving the contrapositive, that if these two groups are isomorphic, then the GCD has to equal 1. So we proved one way of that implication. Let's prove the other. And that one will give a direct proof. Okay, assume GCD of M and N is equal to 1. So we want to now show that it's cyclic. So we claim this is cyclic. And since we've proven that any cyclic group with the same amount of elements, they all must be isomorphic, that would show it's equal to that cyclic group. If that's any cyclic group of Mn elements is isomorphic to that. I should pause for a second. Why does this have Nn element? It's almost a basic probability element. You think of the Cartesian product, you have n choices for what goes in the first component, and then each of those have n choices for what goes in the second component. So if you look at the total number of elements, there are m times n different choices to fill out your ordered pairs. Okay, so let's look at what do you think is going to generate? Well, 1 is a generator for any Zm, for any of the integers mod any number. So let's look at that. Let's look at the order of 1, 1. Okay, so they look the same, but these are two different elements. This is an element in the integers mod m. This is an element in the integers mod n. So let k be the order of this element. So in particular, if we add k to itself, if we add this number to itself k times, on the one hand, we have to get 0, 0. But by the way we add things in the Cartesian product, we'd just be adding each component up to itself. So we would have k, comma, the class determined by k, comma, the class determined by k would have to be the 0, 0. And so what's going to happen here? Let me just rewrite this. So basically we have k, comma, k is the 0 element, and for emphasis, where does that 0 element live? Well, this is the group we're talking about. So what does that tell us? That tells us that k has to be congruent to K has to be congruent to 0 mod M. And also from the set, that's setting this one equal to 0. This is also the 0, this one equals 0. This is equal to 0. So this must be 0 mod n. So what does that mean? With integers mod n, if something's 0, that means the mod has to divide it. So m divides k, and n divides k. So that means I think k is a common multiple of mn. So what we have is we have the least common multiple of n and m must divide any common multiple. So the LCM of mn must divide k. But what is the LCM? What's our assumption? The GCD is 1. So the LCM, if we look at mn, that's just m n, let me try it this way. The LCM of m and n, if you remember, was the product taking out the GCD of m and n. But by assumption, we're assuming that's equal to 1. So the LCM of m and n in this case is just m times n. So thus, mn divides k. Since n times 1 would equal what? Would be, you can think of this as n times m, or even both, just mn. But now this component is mod n, so this is 0, this is mod n, so that's 0. So this will be all 0, 0. So what does that tell us? That tells us that k has to divide mn, right? Because remember, very important fact, if a group element repeatedly applied to itself a certain number of times in the identity, the order of that group element has to divide that power, or the number of times you do that. And again, that's because k is sort of the least power that's going to take 1, 1 equal to 0. That's what k is. K is the smallest integer multiple of 1, 1 that would take you to 0. So k equals mn, and that really completes the proof, right? Because that shows us that element 1, 1 has order mn, so it must generate the full group, and therefore that group must be cyclic. So the order of that element we've just shown is equal to k. We'll define it to be k, which we've shown is equal to mn, which is the order of the whole entire group, and so that group is cyclic, generated by a single element. And then again, because it's cyclic and it has n times m elements, it's got to be isomorphic to m times n. So that proves that the other implication. Should point out the same symbolism means two different things. These absolute value brackets here means the order of an element, and over here we're talking about the order of a group. Though there's a relationship, right? The order of this element is the order of the cyclic subgroup generated by that element. Okay, then there's another theorem we won't state without proof. You can just use this technique with induction that if we have Zm1 plus Zm2, suppose we have more than two of them. Suppose we have S of these. Well, when is that going to be cyclic? When is it going to be isomorphic to Z of M1 times M2 all the way up to MT? If and only if each of these are relatively prime. So the GCDs of Mi, Mj is equal to 1 if we're picking different numbers. So we'll state a couple more results without proof of that. So this proof really is not bad. It's induction proof, and the inductive step, the argument from the inductive step, pretty much is the same argument we used to prove in the 2 case, where Zm cross Zn is isomorphic if and only if the GCD of m and n is equal to 1. Yeah, I'm not going to write it, I wrote it in the notes, I'm not going to write it on the board, but a way of saying this in words is symbolism that the GCD of mi, comma, mj is equal to 1 if I is not equal to j. We'd say all those mi's are relatively prime to each other. There's also another theorem, again we'll state without proof. If G is an abelian group, that has a prime power order, G equals P to the N for a prime P, then G is a direct product of cyclic groups of order P raised to some exponent alpha I for I going 1 to S, where if you add up all the powers, alpha 1 plus alpha 2, all the way up to alpha S, that's going to be your exponent n. So then just like a simple case when we had the 4-element group, 2 to the second, so we certainly had, in one case there's just a single alpha 1, alpha equals 4, so some cyclic groups was just a single group with p to the squared elements, or 2 squared elements, and then when the other case though, you could have alpha 1 be 2, alpha alpha 2 be 1 as well. Alpha 1 be 1, alpha 2 be 1, so you'd have 1 plus 1 equals 2. And if P is 2, P to the first, it would be the direct product of Z2 cross Z2. Two groups with P to the first elements. So again, just in that simple case we've looked at, let's see how this fits in. Let me just restate that again. Again, you have P2 squared, 4. There's a 4-element group. One is just a single group of P raised to the second, 2 raised to the second. The other group is product of two groups, 2 raised to the first, just 2, and 2 raised to the second for the order. And we'll state this without proof because we're mainly interested in an example. If G is abelian with the order of G equals P to the N, then G is a product of cyclic groups of various orders, so cyclic groups are all isomorphic to Zn for some n, or Z to some integer. So then G is isomorphic to, what are the choices? Well, it could be cyclic. Oh, I want to give a specific example. I'm sorry, not P. Thinking of going through the notes, this is P cubed. So that's one choice. It could be a cyclic. How else could we break this up? Well, you could have that sort of 3 equals 3. You could go 1 plus 2 equals 3. So you could have Z P squared cross ZP. And you could also break up 3, the exponent being 3, as 1 plus 1 plus 1 equals 3. So that would be ZP cross ZP cross ZP. Again, the group G itself is a direct product of cyclic groups, but then each of these cyclic groups have to be isomorphic to one of those. Let's look at another example of G being abelian with maybe one higher, P to the 4th. So let G be an abelian group with the order of G equals P to the 4th for P prime. I'm thinking now I did not state that here in this example. That is only true if P is a prime. Because that guarantees the GCD of these is not going to be 1. And so we kind of can't collapse ZP cross ZP will not be isomorphic to ZP squared. Now the question is, maybe these two groups really are the same as this. But no, because this group is cyclic, this group would only be isomorphic to this group if the GCD of P and P is 1, and that's not the case. So you actually do have different groups there. Okay, so let's look at the possible classes then. G is isomorphic to one of, so G could be cyclic. Or G could be ZP cross Q cross ZP. Or G could just be 4 copies of ZP. Or it could be ZP squared cross ZP squared. And I think I got them all. 1, 2, 3, 4. I think there's one more, but we also could have a ZP cross ZP cross a ZP squared. So we could have that as well. So those are some examples of a cyclic group. So those are possible isomorphism classes. And again, you notice that this has a lot to do with something that's called a partition. You look at 4, the exponent. You think of this as 4 equals 4, 3 plus 1 equals 4, 1 plus 1 plus 1 plus 1 equals 4, 2 plus 2 equals 4, 1 plus 1 plus 2 equals 4. So there's kind of some fundamental relationships there on arithmetic. And so the number of ways to add up a positive integer n is called a partition. So in general, the number of ways to represent an integer n as a sum of positive integers is called the number of partitions. Right, so each way of representing an integer would be called a partition. So what we've really shown, and that's a simple fact, grade school. Now let's go to undergraduate, senior level undergraduate mathematics. The number of isomorphism classes of an abelian group with p to the n elements for p prime that's actually going to equal the number of partitions of n. When I say isomorphism class, what I mean, remember, isomorphism is an equivalence relation on the set of all the groups out there in the universe. You can take two groups as being equivalent if they're isomorphic. And so we've seen any equivalence relationship will partition the set into classes. So that's what I mean by an isomorphism class. It's all groups that are isomorphic to each other. So we also stated another theorem without proof. If G is an abelian group, with order G equal n, where n has prime factorization as follows, say n1, p1, n1, P2N2 dot 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 PTNT for distinct primes P1, P2, all the way up to PT. Then what we have is the following. Then G is equal to AP1, direct product with AP2, direct product with, say, APT, where the order of API is equal to PI to the NI. So we'll look at this in an example. But basically what that's saying is, okay, we see how we can decompose elements that, say, have 5 to the third, right? 5 is a prime group. And then we've also seen how we can, but now suppose we had an element that had 5 to the third times 7 elements, a group that had 5 to the third times 7 elements. That could be broken down into 2 groups. One group would have 5 to the third elements. One group would have 7 elements. And then we can further break those down because now the 5 to the third is in this case. So we'll look at this as an example right now. Let G be an abelian group with 72 elements, which is 8 times 9, which is 2 cubed times 3 squared. So what we can do is we can sort of break, we know that G has to equal A1 cross A2, where A1 has 8, or 2 to the third elements, and A2 has 9, or 3 squared elements. So A1 is isomorphic to one of how many different groups? Well, I'll put it in groups. I'll leave this blank. Let's, for a second, so I count. So if you have 8 elements, you could be cyclic, Z4 cross Z2, Z2 cross Z2 cross Z2. 3. And we've actually seen that in the example with the various choices. And that's it. While 3 is 3 squared, A2 is isomorphic to one of 2 groups, either Z9 or Z3 cross Z3. So G itself, a 72 element order group, there's sort of 3 choices for what this group can be isomorphic, each of which has 2 choices for what that group is isomorphic. So G is isomorphic to one of 6 groups. And what are the 6 groups? Well, pick one of these 3 to go here, cross pick one of those two to go there, and those are your 6 groups. Okay, so let's get some definitions or restate some facts. So a homomorphism is what I call an operation preserving map of a group G into a group H. By operation preserving, that's just the definition. You can multiply the 2 elements in G together first, put them into the homomorphism, get your result in H. Or you can take those same 2 elements and multiply, put them into G first, get your 2 elements of H, and then multiply, you get the same result. And we've defined an isomorphism is a homomorphism. It's a special type of homomorphism that has 2 characteristics, is 1-to-1 and onto. Now we get, so those are review. A new definition is an automorphism. An automorphism is an isomorphism basically from a group G to G. From a group onto itself. So homomorphism would be, isomorphism it goes between 2 different groups, not necessarily the same, but no restriction, they could be the same. When they are the same, that's a special type of isomorphism that we call an automorphism. So let's look at an example. Given a group G, we define phi of G, not quite there yet. So let's give me a group. I need more than just a group. You gotta give me a group and an element for this definition. So give me an element A and G. Define a function phi of G by A inverse GA for all G in G. That mapping is an automorphism in G. Is an automorphism of G. And it's actually called the inner automorphism determined by A. So this will be the last thing I'd like to do because I'm about to get kicked out of the library. So let's show why this is. Let's first show its operational preserving. So let phi of G and H would be what? A inverse GH. Okay, there's a parenthesis here, but I don't really need to put the parentheses because it'll be commutative. And then I can put an A inverse in between any elements. And again, the parentheses, because of the associativity, well, I can just group my parentheses anyway, right? Because these two multiply together to give you an E. G times E, for instance, is just G. But that's just going to be phi of G times phi of H. This is true for all G and H and G. So phi is a homomorphism of G into G. Why is it into G? Why is this in G? Well, A is in G, G is in G, A inverse is in G, so this inverse and product, this has to stay within the group. Because A and G are both elements of the group G, so certainly that would be. So let's show it's onto. Take any G in G. Certainly we have A, G, A inverse is an element of G. And if we look at alpha of A, G, A inverse, by definition we multiply anything we stick into alpha, we multiply on the left by A inverse, on the right by A, and that's just equal to G. And that's enough to show alpha's onto, right? Because you give me any element G figure that as being in the range, even though the domain and the range are the same. But think about G as being an element in the range. I've now got something in the domain that phi of G is going to hit. So any element of G, I can map something to it. That's what it means to be onto. So I've got a homomorphism from G to itself. I've got an isomorph. I've got a one-to-one. The last thing I have to show is one-to-one. So suppose phi of G equals phi of H. By definition, that means A inverse GA is equal to A inverse A inverse HA. Which will mean if we multiply by A on the left and A inverse on the right to each side, so then this is alpha of H, so there should be an H here, an H here. Well, those are just the identities, so basically we have E, G, E equals E, H, H. So G equals H, and phi of alpha of G equaling alpha of H implies G equals H, which just means alpha is 1-to-1. So the inner automorphism phi of G equals A inverse G alpha is an automorphism of G. And I think I may have to wrap up now. So we'll continue talking about this in future lectures.